Welcome to your first instructional video. At this point, hopefully you guys have looked through the syllabus, you've watched that first video over like how to work Canvas, how to work Pearson, and now you're ready to learn. Well, the first thing we're going to be talking about is a concept called limits. In order to understand calculus, you have to be able to understand what a limit is. So we're going to introduce this, we're going to look at it on a graph, and we're really going to answer this question of what is a limit? Well, the definition I'll give you is as follows. A limit answers the question, what happens to a function as your x value approaches a certain number? So let's look at an example. Here we have a nice simple linear function of 2x minus 1. But what if I wanted to know what's happening to the function as I approach this value of 3? Well, to write that as a limit, I would write LIM for limit, and then under that I would write x arrow 3. And that's saying what's happening as x approaches 3. So x is approaching this value of 3. And what's happening to my function? So what's my limit of f of x? Well, what's happening? If I look at this function, right? If I approach 3, if I approach from this side, my value is getting closer and closer to this y value. And that's also true if I approach from this direction. So as I approach from that direction, same thing is happening as I'm approaching this y value. What's that y value? That y value is 5. So I would say the limit as x approaches 3 of f of x is just equal to 5. Well, guess what? That's just the corresponding y value for when x is 3, right? You can get that just by plugging in 3 to the function. 2 times 3 is 6, minus 1 is just 5. So what's the point? Why do I actually need limits when I can find that by just plugging it into the function? Well, there's actually two big reasons why limits are important. Well, there's actually two big areas where we like to use limits, where they become very helpful. So, and these two circumstances are, well, what if the x value approaches a number where the function is not continuous? We call these discontinuities. So that's what these are called. So that's where limits can be helpful, because with the discontinuity, you can't actually plug your function in. Or you can't actually plug a value into your function because a lot of the times your function's undefined at that point. And the other area where limits are important is, what if x is approaching infinity? In limit notation, that would look like this. If I let x approach infinity, what happens to my function? So limits are important here because I can't actually plug infinity into my function. So that's where limits are important. So let's look at an example now. So here we have a really fun function with lots of stuff going on. In fact, we call this a piecewise function because you can kind of split it up into pieces, and depending on which piece you're looking at, the rule is different. So the rule changes based off of what x value you're looking at. But it's all one function, where all of this is f of x. And what we're going to look at is, where might I want to look at the limit? Well, first off, where do I have discontinuities? Well, if I look at -3, we can see I've got a little open circle at -3. So that counts. That's a discontinuity. What about at -1? -1, I've got a discontinuity as well. Because if I try and plug in -1, I don't get a defined value out. And last, remember, discontinuities are places where you have to pick up your pencil. The last place I need to pick up my pencil is here at +2, right? So I have 3 discontinuities of this function. There's 3 discontinuities in this function. And let's look at each of these. Okay, let's start with x equals -3. Well, like we said earlier, this is where limits become helpful. because now I can ask the question, what's happening to my function as I get really, really close to -3? What's happening to my function? Well, if I approach from this side, I approach this y value of, I don't know, 2.7. And if I approach from this side, same thing happens. I'm approaching a y value of about 2.7. So I'd say my limit is equal to 2.7. Now, of course, that's different than what the actual function value is. If I try and plug in -3, I have an open circle there, and my function value doesn't actually exist. Well, we consider this, the name of this type of discontinuity is a hole discontinuity. Or the other word you'll hear it called is a removable discontinuity. Because it looks pretty much like a continuous function except for that open circle, except for that hole. So that open circle represents. Okay, well, let's move on to the next type of discontinuity. Let's look at what's happening at -1. Well, what is my function approaching as I approach -1? Well, if I come from the left side, my function is shooting down to -infinity as I approach -1. But if I come from the right side, my function's going up to positive infinity. Interesting. So at -1, it actually depends on what direction I come from, because I'm getting two different things. I'm getting two different types of infinity, positive infinity and negative infinity. So how do I write that? Well, it turns out I can actually denote that by using a little plus or minus sign. So I'm going to put a little plus. I'll start by putting a little plus in the top corner of -1 to show, let's approach from numbers that are more positive than -1. If it's more positive, that means I'm approaching from the right side, because the right side is more positive values. And in that case, what do we decide? If I approach from the right side, my function is approaching positive infinity. But then if I change this and change the direction, so now I'm going to approach from the negative direction. Sorry, let me mark that in red. That represents coming from the left side. My limit is different. Now I'm approaching from now my function goes to negative infinity, right? We can see that right here. As I approach from the left side, my function's shooting down to negative. Well, because, let's go back to that original question where I didn't specify a direction. Because the limit is different depending on what direction I come from, then this limit actually doesn't exist. That means if I don't specify a direction, it's impossible for me to answer that question because I don't know whether to say negative infinity or positive infinity, and I would say it doesn't exist. Well, what do we call this type of discontinuity? Well, because my limits are going to infinite values, I call this an infinite discontinuity. Okay, you'll also hear this. Oh my goodness. You'll also hear this called a vertical asymptote. Hopefully that word asymptote sounds familiar, because that's something you've probably seen before. Okay, well, we do have one more discontinuity. Take a look at the limit as x approaches 2 of my function. What's happening to the function as I let x approach 2? Well, the same thing happens where depending on what direction I approach from, my function is approaching two different things, approaching two different values. So if I come from the negative direction, if I come from numbers less than 2, which is, remember, that means I'm coming from the left, I'm approaching a y value of 3. But then if I come from the positive direction, what is my function approaching? My function approaches a value of 4. So once again, I get two different values for my limit depending on what direction I come from. Which means that if I don't specify direction, once again, if I don't specify direction, then the limit doesn't exist. This one's slightly different than the one before. We called the last one an infinite discontinuity because my limits were going to infinite values. That's not the case here. My limits actually go to finite values, but they don't go to the same value. So for that reason, we call this a jump discontinuity because the graph jumped there at 2. Now, some of you guys might be saying, wait a second, isn't there one more? Don't I have a discontinuity here at 1? Well, I actually don't because I have a closed circle there. And from either side, the function is going to the same value. So that's still, that my function still continues there even though I have a weird angle. It's still continuous there. Okay, so that takes care of my discontinuities. And as we did, we looked at the 3 different types. So there's 3 different types of discontinuities that we work with. We work with holes, infinite discontinuities, and jumps. Well, we also talked about how limits are important for what happens to the function as it approaches infinity. Another name for this is end behavior. What's happening at the end of my graphs? Well, let's take a look at my function and see if this function has end behavior. What's happening to my function as I let x approach infinity? Well, letting x approach infinity means I'm letting x get infinitely large. What's happening to my function as I let x get bigger and bigger? Well, we can kind of see that the function flattens out at this value. It flattens out at a y value of 2. So, what I would say is my limit as x approaches positive infinity of my function is equal to 2. My function approaches a y value of 2 as I let x get infinitely large. Well, let's go the other direction. What's the limit as x approaches negative infinity? It's looking this way. What's happening as my x values get infinitely negative? We can see that my graph approaches this value, 3. So in this case, my function also approaches a finite value as I go to the left direction. Okay? So this is my end behavior. You can also call this horizontal asymptotes because your graph is approaching a finite value as I let it go off to infinity. This isn't always going to be the case. There's plenty of functions where if you let x get infinitely large, the y value also gets infinitely large. So this isn't always the case, but some functions will have these horizontal asymptotes and have end behavior that I can look at with limits. Well, up to this point, we've introduced this concept of limits using graphs, of looking at what the function is approaching, what is the function approaching visually, right? Being able to see what's happening to the function as it approaches a certain x value. But what if we don't have a graph? That's not always going to be given to us. Can I still evaluate limits without relying on a visual tool, right? Without being able to visually see what the graph's doing. Well, that's a big part of what we're going to be talking about in 1.2, but we're going to start talking about in 1.1 with piecewise functions. Piecewise functions are a great example of or a more straightforward way to look at limits without graphs. If you remember, piecewise functions are functions that have different rules depending on what x values you're working with. So look at this example. You'll notice I use this big squiggly bracket for piecewise functions because the rule is equal to x minus 2 if x is less than 3, but it changes to this new rule of negative 1/3 x plus 4 once x is greater than or equal to 3. So I've got two different rules depending on what your x value is, and this dividing point is x equals 3. Once you're past that, then the rule changes. So there's my piecewise function. And why would a limit be helpful here? If I look closely, right, the two rules that I'm working with are relatively simple, right? They're both just linear functions. And what we talked about earlier at the very beginning is if you have a simple enough function, then the limit is, all you need to do is just plug in the value for the limit. So why would I need a limit here? These functions are continuous for all values for all x values that I try and plug in. There's really only one exception to this, and that's where the rule changes. That's the only possible place where I could have a discontinuity, because the rule changes from one thing to another at this specific x value. So there's a chance that maybe the two rules don't actually match or connect. So we're going to figure out if there's a discontinuity at x equals 3. That's what we're going to figure out here, and we're going to use limits to help me figure this out. So that means I want to find the limit as x approaches 3. Okay. Well, if I'm taking the limit as x approaches 3, I'm looking at what is the function doing as it approaches 3. Well, depending on what side of 3 you're on, if you're looking at numbers less than 3, the rule is different than if you're looking at numbers greater than 3, which means I need to approach this from two different directions. We're going to approach this from the negative direction and the positive direction. We're going to look at what the function's doing from each of these directions. Let's start with this negative direction. If I'm looking at numbers strictly less than 3, right? They're getting close to 3, but it's numbers that are slightly less than 3, like 2.9, 2.99, right? Numbers that are just barely less than 3. If I'm using numbers less than 3, which rule am I applying? What rule do I need to be using? Since x is less than 3, I'm looking at this rule, x minus 2, which means that this limit, I can replace g of x. Since I'm only looking at numbers less than 3, I can replace g of x with just that function right there, that specific rule. Well, once again, since that's a very simple linear function, then to evaluate that limit, all I need to do is just plug in 3. Plug in the value that I'm looking at and see what happens. And so this gives me 3 minus 2, which equals 1. So that's what my limit is equal to if I'm approaching from numbers slightly less than 3. Okay? And notice we didn't need a graph to do that. I did that just by plugging the value into my function. Well, shouldn't that mean that my other limit's 1 too? Well, no, not necessarily, because for this limit, for my other limit, I'm approaching from numbers greater than 3, which means I'm not using this rule anymore. I'm not using x minus 2 anymore. Instead, I'm using the bottom rule because I'm looking at numbers that are slightly bigger than 3, which means I use the other rule. So this limit is equal to the limit of this function, because I know I'm only using values greater than 3. Well, once again, this is a nice simple function, which means to evaluate this limit, I can just plug in 3 and see what happens. Negative 1/3 times 3 is negative 1. Negative 1 plus 4 is positive 3. So interesting, I get two different values depending on what direction I come from. What does this tell me? This tells me if I approach from the left, my y value, here, let me actually draw a picture of this so we can visualize this. So this means if I approach from the left, my function is approaching 1. But if I approach from the right, my function is approaching 3. Is my function continuous? No, because the rules don't connect at x equals 3. They don't actually connect. What type of discontinuity is this? This is a jump discontinuity. So it's not continuous, and this is what we'd call a jump discontinuity. Perfect. Okay, good luck with your 1.1 homework, and then in 1.2 we'll talk some more about how we can use algebraic manipulation to be able to evaluate limits more without having to use a graph. Okay, good luck, guys.